Yeah, thanks. Thanks for being here. Quite crowded. That's good. Um, yeah, I'd like to talk about how we in Danfoss use system simulation in a quite pragmatic way in the area of data center cooling. And today we want to have a special focus of how we can find an optimal way of use the heat recovery potential of a data center. So let's directly jump into the topic. My name is Timo Schubert. So I'm a data center simulation specialist in Danfoss Climate Solutions. And that's maybe the little bit interactive part of the presentation today. Who of you knows Danfoss? Maybe you can raise your arm. Oh, okay. Surprisingly, yeah, a lot. Now it's the tougher question. Who knows more than one product we are selling, and radiator thermostats don't count? Maybe also, can you raise your arm? Now it's getting difficult. Yeah. So Danfoss is a component manufacturer, and Danfoss Climate Solutions produces everything in the area of heating and cooling. So we are selling compressors, we're selling heat exchangers, we're selling valves, we are selling hoses, quick disconnectors, controllers, sensors, so everything what you can find in a heating and cooling system. We're teaming up here in this presentation together with TLK Energy. I think I don't have to introduce them. They're quite, known for their expertise in system simulation for energy systems. And they are represented here with Manuel Gräber and Dominik Hering. So how and where are we using Modelica and Danfoss? So General Danfoss consists of three sections, and as I said, the one where I'm working in is Climate Solutions. And there we have a system simulation team where we use Modelica, we use a lot of the FMI standard, and on library side, we're using the TIL suite from TLK and the Linux library from Lawrence Berkeley Institute. We are looking on the topics we identified more or less on our growth areas, the sector coupling, food industry, heat pumps, and today we're talking about data centers. So at the moment we're 8 people in the core team for system simulation. We are growing. Maybe some of you saw that on LinkedIn. We are hiring at the moment. And there are also some more single users across the whole company. And whenever we need support, we have a partner, TLK Energy, on our side. So they support us in projects, but also in the model and tool development. By the way, sorry for my voice. I lost it somehow yesterday in the boat. Let's jump into the topic. So enough for the promotion and the introduction. We want to have a look at exemplary data center. And we want to find out what's the best way of recovering the heat of the data center. So we have the question is always why can we as Danfoss spend money to have a team simulating data centers? And if you have a look at this graph, it's quite easy to find out, right? So it's expected that the installed IT capacity and also the electricity demand of data centers globally will double by 2030. So we will end up at approximately 950 megawatt hours of electricity consumption in a year in 2030, which is more or less what Japan as a whole country consumes at the moment. And if we consume this, with this amount of electricity, it always comes together with a lot of CO2 emissions, right? 2.5 billion metric tons is, the number we have here. And because there is a lot of environmental impact, also, institutions like the EU start to regulate the market. So in the EU, we have the Energy Efficiency Directive, which tells us for every data center which has a IT power demand for more than 500 kilowatts, which is nothing. So it's tiny if you have a look what kind of data centers are built at the moment. They have to report on annual basis their KPIs for sustainability. And if you double the size, so 1 megawatt, still a tiny data center. It says it should use excess heat. And those data centers have to be located, if possible, where XST can be reused. And this together, so the growth and those regulations, let's us expect that there will be a lot of investments for the decarbonization of data centers in the next years. So this can be done in different areas. And one we want to look at today is the XST recovery. So to make it short, Danfoss thinks we can make a lot of money there. So what's the situation we are dealing with at the moment? So every new data center, which is used for AI applications or high performance computing, is more or less a liquid cooled data center. Why? So if we have a look, one single rack of NVIDIA at the moment, which is, I would say, more or less the standard, has a heat release of 130 kilowatts per rack. If you have a look at the next generations, so the next 2-3 years, we're talking about 200, 600 kilowatts per rack. This is an energy density you cannot use air anymore as a heat transfer fluid. The heat transfer is not good enough, and also the heat capacity of air is just simply not good enough. What does it mean? So at the moment, we are talking about a heat dissipation of one GPU on a surface of approximately a credit card. And the cold pipe on top of it has a volume of approximately 100 milliliters, not really more. So that's the situation we're dealing at the moment. And if you look back 10, 15 years, people were talking about temperature levels for this liquid cooling of 50, 60 degrees C. So that would be a dream for heat recovery, right? But nobody's talking about this anymore. So if you talk to the main silicon suppliers and also the hyperscalers, so the Metas, Googles, Microsofts, we're talking more about 30-degree temperature supply. So what does it mean for our heat recovery? So 30 degrees are not really high, right? So we cannot really reuse it directly. So there are few applications, but okay. So we have to somehow shift up the temperature level. And what the technology do we have for this? It's typically a heat pump. So let's look at our use case. So we thought, okay, let's take a 2.4 megawatt data center, still small, right? Could be a small data center or a research institute or whatever, where we have our data hall with our liquid cooled IT equipment. Yes. You see up there is also a liquid air heat exchanger. Why? You can always cover more or less 80% of the dissipated heat. You can cover this with liquid cooling. There's always some dissipation into the air, and then you have to cool down the air. That means we need 2 temperature levels for the cooling cycle. So our liquid cooling part here, there we are at our 30 degrees. And the upper line is our air cooling part, where we need lower temperatures. So it's approximately 20 degrees. And now the question is, we want to recover the heat and feed this nearby office building then. How do we do it? We could either place the heat recovery system on top, save some chiller power here, which is connected to the air cooling loop, or we connect it here to the bottom, use the higher temperature, and save some fan power for the regulars. What's the best? That's the question. And system simulation can help us out here. So what did we do? We modeled this entire system, really from the heat dissipation of the racks up to the chillers, dry coolers, heat recovery, and the office complex as a heat consumer. On the left-hand side, we still make TLK. So we created this office building to determine the heat demand. On the right-hand side, we somewhere else, modeling the cooling system itself. Well, I forgot, we put it together so that we are all well. So that's our model of the cooling system, right? So we have again our heat sources in the data hall, our 2 cooling loops, the chillers, the dry coolers, and the heat recovery system here with the heat consumer in there. And again, a little bit promotion. So you see in the subsystems here, a lot of our components are in there. What we have, more or less for every component we have validated component models. So that are part of our subsystem models there. The office building was modeled in 3D, then translated into a zone model. So the overall office consists of approximately 250 zones. So the model has or has more or less or has all relevant physical relations or equations in it. So it considers solar radiation, convective and conductive heat losses, ventilation losses, and also internal heat sources. And yeah, putting weather files on top of it as boundary conditions, we can determine the heat profile over the year. And we end up here with a peak heat demand of 800 kilowatt. So at a pretty cold day in winter time. And then we started to simulate 4 scenarios. Our benchmark, our reference is a situation where we don't have heat recovery. That's what we want to reference. Then we have option A, where we connect the heat recovery system to the cold part here, and then to the office complex. Option B, we do it here and connect it. And then there's a differentiation. We can do it either with a heat pump with 1 compressor in it, so approximately 400 kilowatt cooling capacity, or with 2 compressors in it, 800 kilowatt capacity. And for sake of time, let's have a look at the very condensed results. And you could be disappointed when you look at the first rows, right? So on the data center side, you see we save nothing, 1 to 3% of electricity. So why? We have a data center in a quite moderate climate. Over the year, there is the compressor is running really, really rarely. So what we do is we save fan power for free cooling, and somehow it is compensated due to additional pumping power we need for the heat recovery side. That means also that our main KPI, so PUE, which is the KPI for data centers for energy efficiency, stays more or less the same. We don't really, only on the data center side, we also don't really save money. So people could say, why should we do heat recovery? But it looks, or it makes sense to look a little bit deeper under the surface, right? So if you have a look at the heat we are providing to the office building, it's a little bit more than 1,000 megawatt hours, which means that we're covering 88% of the heat recovery of the heat demand of the building. That means that we are approximately 4% of our electricity consumption we are having in the data center is now reused for heating. That's a small number. So normally you would like to go up to 10%, 15%, but you have to live with the heat demand you have, right? So not possible to squeeze out more or too much more. Our heat pump is consuming 300 in 30 in option A megawatt hours electricity, and option B is a little bit less, 270 280 megawatt hours. So that means that we end up in an average or seasonal COP of the heat pumps of 3.1 for option A, 3.8 for option B, 3.7 for option B with the 2 compressors. That means that we have some kind of 5 cents, 6 cents generation costs for our heat recovery, for our district heat. It's no transmission costs, nothing in it. It's the pure generation cost, which is, at least in Germany, quite compatible. It's quite cheap. And if you have a look at the last row, you see, okay, we are saving 50 tons, approximately 70 tons of CO2 compared to a situation where this office building would only use district heating with the average CO2 emission factor of, what did I say, 180 grams per kilowatt hour. So I think we could say, it makes sense to use heat recovery, right? So maybe not on the data center side or on the very front page of it, but if you look deeper into it, it's a good thing. We still have the question open. What is our best option? And you see it's relatively, I'm not allowed to tell prices, that's why. But what we can say is option B large, which is our model, it's our situation where we have 2 compressors in the heat pump, is significantly more expensive than the one when we only have 1 compressor in the heat pump, right? Compressors drive the price. Option A and B are more or less same expensive, so the investment costs are similar. If we now compare option A and option B small with the one compressor and the heat pump, we see, okay, we are able to recover slightly more of our energy consumption of the data center with option B. We can produce our district heat a little bit cheaper, and we're saving more CO2. So unsurprisingly, our proposal would be that we realize it like this. So we have our data center again, and then we take our heat from the hot cooling cycle, have our heat recovery system here, and feed it into the local district heating network. We choose the small version, so compressor. That means we have a heat recovery unit here, which is a valve and a heat exchanger, capacity approximately 400 kilowatts. And we have another heat exchanger with a valve here, the substation to the district heating network, 500 kilowatts capacity, and our heat pump here, one total core compressor. So here we have also 400 kilowatts cooling capacity, 500-ish kilowatts heating capacity. Yeah, so we're not really at the end of the story, right? We still could say, how can we improve the system further? For example, you saw, okay, we are recovering 88, 87% of the heat. This is mainly because our compressors cannot go under a certain part load ratio. So we can't really use the low part loads. Simple solution or common solution for this would be, let's implement heat storages, right? So that we can further increase this ratio. And also, we saw now here, we're using quite a lot of pumping power. And just by improving our control strategy here, using those valves only when necessary, it could also save us some money, some electricity for the electricity. But I see I'm very, very good on time. Let's already wrap it up. We can see that for this slightly small system, right? It's some, let's say, showcase. Real systems can be significantly more complex. But for this system, we could show, okay, system simulation helps to find a good solution for heat recovery. We have facts which we can use as basis for discussion. We are using our validated components models, which means that we are quite confident that our first guesses for efficiency are quite accurate, even in the very beginning. And also, very, very important part is the third one. So to properly size the system, properly choose the correct option, it's important that you have good, realistic information about the consumer profile. So as you saw, we have peak loads of 800 kilowatts, but we're sizing the system now for 400 kilowatts, 500 kilowatts, which is more realistic in terms of financial reasonability of this. We are using not specifically this model, but those kinds of models internally as benchmarks. So if somebody of our application engineers has an idea to improve the situation, they come to us and say, okay, let's replace a certain thing in the system and see how it performs. And what we are also doing is having some white paper style use cases which we can present to customers, show our knowledge in the area, and also help our sales people then. Speaking of sales, if you want to know more about Danfoss data center solutions and also the heat recovery solutions, you can, I think, download the presentation and click on the links. And the same is for TLK's activities, for waste heat recovery, and also the building performance simulation by the TLK or SPC, how the joint venture is called. Have a look, and very much on time. Thanks for your attention.